Hello students, it's me. In today's lesson, I will explain the concept of airbags in relation to topic 1.3 in IB Chemistry HL. The subtopics are gas laws, moles, molarity, and percent yield. Here are the takeaways from this lesson. You can pause the video right here to take a look at the content that I will review. I will start by introducing the mechanism of airbags. You guys may wonder, what is an airbag? Well, an airbag is a device that reduces the driver from receiving any injuries upon collision. When a car is rapidly slowing down, airbags are electrically ignited by a sensor. And next to it, sodium azide rapidly decomposes into nitrogen gas and sodium metal. The nitrogen gas quickly fills the bag to protect the driver from collision. I will now explain how Charles' law explains the cushioning effect of airbags. As we all know, volume and temperature are directly proportional at constant temperature. This can be modeled by the equation V1 over T1 equals V2 over T2. V represents volume while T represents temperature. Upon the collision of a car, hot nitrogen gas quickly fills the airbag, which then causes it to inflate. As the temperature is extremely hot, the gas expands at a very rapid rate. However, the exterior temperature is significantly cooler and the gas cools rapidly. This cooling consequently causes the volume to slowly decrease, which creates a cushioning effect which protects the driver's face. Alright guys, now that you've understood the basics of airbags, let's try to create one. Don't forget to put on your safety goggles, lab coats, and tie your hair back, ladies. Oh no, our laboratory does not have any sodium azide. Oh no, our laboratory does not have any sodium azide due to insufficient funding. Good thing the reaction between hydrochloric acid and NaCH3 or isodium ethanoate will be used as a substitute. Here's the question that we will try to solve together. Tonkla wants to generate 0.9 liters of CO2 gas to fill the airbag. What volume of 11.65 molar hydrochloric acid would be needed? Here we go, students. We must first deduce the equation of the reaction. What do you guys think it is? Here's a hint. It's a reaction between an acid and a sodium carbonate. That's right. The reaction yields water, carbon dioxide, and sodium chloride. Now that you've gotten the general equation, I will give you the overall picture of what we will go through. Let's read the list. Here's the overall process. Firstly, we will find the moles of CO2, and then we will use the moles of CO2 to find the moles of hydrochloric acid. From the moles of hydrochloric acid, we can then deduce the volume of hydrochloric acid required to produce 0.9 liters of carbon dioxide gas to fill the airbag. And then, after we have conducted the experiment, we will then find the percent yield by comparing the theoretical and the experimental values. Let's start by solving for the moles of carbon dioxide. To do this process, we will be using the ideal gas equation, which is PV equals nRT. We are trying to find N, or the number of moles. P represents the pressure in ATM, V represents volume in liters, N represents the mole of gas in moles, and T represents the temperature in Kelvin. Do not forget that it must be in kelvins. And R is the universal gas constant, which is 0.08206 liters ATM over mole Kelvin. I have added the general equation of this question on top in case you guys forget. Let's start by looking at the given values. We are given that the experiment is conducted at 1 ATM and the volume that we are trying to achieve is 0.9 liters. The universal constant is 0.0821 liters ATM mole Kelvin, and the temperature is conducted at 22 degrees Celsius. Firstly, we will rearrange the ideal gas equation to isolate moles on one side as we are trying to find that value. The rearranged formula is N equals PV over RT. Next, we must convert temperature, which is currently in 22 degrees Celsius, into kelvins, and we simply do that by adding 273 and 22, which gives us a value of 295 Kelvin. Now that we have all the values, we substitute them into the rearranged ideal gas equation. And if you guys try to type these numbers in the calculator, it gives you a value of 0.0372 moles of CO2 that is required. Great job, guys. Now that we have the moles of CO2, we can now find the moles of hydrochloric acid. From the equation, it can be seen that there is a 1 to 1 to 1 to 1 to 1 to 1 ratio between all of the compounds. And there are also no limiting reagents, as it is all a 1-to-1 ratio. We were lucky there. From the equation, we can see that there is a 1-to-1 ratio between carbon dioxide and hydrochloric acid. As such, the same amount of moles between carbon dioxide and hydrochloric acid is required, which is 0.0372 moles. Now, we can find the volume of hydrochloric acid required. But first, I must introduce you guys towards the concept of molarity and concentration. Concentration is the amount of something per volume. On the other hand, molarity is the number of moles per unit volume of a solvent. The general equation is N equals CV. N is the number of moles, V is volume, and C is concentration. However, moles and concentration are not the same because concentration is the ratio of the amount of solute per amount of solution, while molarity is a unit of concentration that relates the number of moles of a solute per liter of solution. Now that you guys have understood the concept of molarity and concentration, let's apply it to this laboratory experiment. It is given that we have 0.0372 moles of hydrochloric acid, and the concentration that is given is 11.65 molar of hydrochloric acid, and we have to find the volume of HCl needed. To do that, we simply substitute the two values of N and C into the formula. And after you have divided 0.0372 by 11.65, it gives you 0.00319 liters of hydrochloric acid, or 3.19 milliliters of hydrochloric acid. Oh no, only 0.75 liters of carbon dioxide was produced in the experiment. Let's use our experimental value to find the percent yield. The percent yield is deduced by dividing the experimental yield by the theoretical yield and multiplying it by 100. The experimental yield of this experiment is 0.75 from conducting the experiment, and the theoretical yield is 0.9 liters. After substituting the two values into the equation and multiplying it by 100, it gives you a value of 83.33%. We have now accomplished our goal. If you guys have any questions, you can direct message me in email. Thank you.